an approximation algorithm for directed Sparsest-Cut on planar directed graphs. This is joint work with Ken-Ichi Kawarabayashi. So let me briefly discuss what are the main results of this paper, and then I will get into some technical details and have some historical remarks. So what we show is that the Sparsest-Cut problem can be approximated to within polylogarithmic factors on directed planar graphs. So in particular, for uniform directed Sparsest-Cut, we get log square approximation. For general directed Sparsest-Cut, we get log to the third. And by similar techniques, we also get a log square approximation for directed multi-cut on planar graphs. And all of these run in polynomial time. In fact, they follow by rounding the classical linear programming relaxation for Sparsest-Cut problem. Now, the main point here is that prior to this work, there was no non-trivial way was known to round this LP for directed graphs, for any class of directed graphs, any non-trivial class. So these are in particular, these are the first polylogarithmic approximation algorithms for the planar case. So the previous bounds were at least polynomial. And the main technical tools are a new multi-commodity Flowcat gap for planar graphs, which I will explain in a moment what it is. And this is obtained using tools from new tools for the theory of ellipsis embeddings that we extend to the case of quasimetric spaces. So these are generalizations of metric spaces to the directed case. These are the objects we need to study to be able to round the LP relaxation to the directed case. All right. Now, let me begin by briefly reminding you what is the Flowcat gap. So this is a generalization of the classical max flow min cut theorem, which asserts that if you have only one commodity, the max flow is equal to the min cut for any graph. Now, this is not true if you have even three commodities. This equality breaks, so you only get a weak duality in this case. So the right way to study this problem in the case of multiple commodities is the notion of Flowcat gap. So what is this? So this is the ratio of the maximum concurrent flow over the Sparsest-Cut. And the maximum concurrent flow is the maximum fraction of all demands that can be routed simultaneously. The Sparsest-Cut is the ratio of demands, capacity over demands, crossing a cut, over all cuts. Now, the first important result, so this parameter has been studied extensively within computer science. It has a lot of applications in the theory of graph partitioning algorithms, and consequently in the theory of divide and conquer algorithms for graph problems. So the one important seminal result is by Layton and Rao, who showed that the gap is logarithmic for the case of uniform demands, which is in fact tight for constant degree expanders. Now, this implies immediately that so this result was used to round the LP relaxation for uniform Sparsest-Cut and obtain a log n approximation algorithm. This was extended to the non-uniform case, so general demands by Linear London and Rabinovich, who also showed a logarithmic upper bound on the gap for the general case. All right, now the notion of the multi-commodity gap is very closely related to ellipsis embeddings. So let me briefly say that it has been shown by Linear London and Rabinovich that it is exactly equal to the infimum distortion required to embed an endpoint metric space into L1 space, also known as Manhattan space. And this is really one of the key results that propelled the theory of bi-ellipsis embeddings into a central role in the toolbox of algorithm designers. Now, let me also mention that this line of research has been extended to rounding semi-definite programming relaxations for the Sparsest-Cut problem. The first people who managed to do this were Aurora Rao Vazirani, who got a square root log n approximation for uniform Sparsest-Cut. This has been extended to the general case by Aurora Linaor, and interestingly, the rounding is also obtained via bi-ellipsis embedding, but this time of metrics of negative type into L1. So these are the objects that one obtains as the solutions of the semi-definite programming relaxation for Sparsest-Cut. All right, now all this is great for undirected graphs. What about directed graphs? It turns out that for directed graphs, the situation is very different. So it has been shown by Tsuzoe Kana that the gap is at least polynomial in the general case by an ingenious construction. And in fact, the result also shows that the problem is hard to approximate within polynomial factors. So in general, directed graphs, the problem is in a sense hopeless. Now, what is also interesting is that there is a connection between the gap and planar graphs that has been studied extensively. So the first result of this type was the very important result by Klein, Plotkin, Rao, who showed that the gap is constant for the case of uniform demands for all classes of graphs that exclude some fixed minor, so all H minor free graphs. And this is obtained by a technique very closely related to bi-ellipsis embeddings, something called ellipsis random partitions, which I will briefly discuss. Now, for the general case, this is open. This is a well-known planar embedding conjecture for the case of planar graphs. Whether the gap is constant or not, we don't know. It's a central open problem in the theory of metric embeddings. And in fact, there is an even stronger conjecture by Gupta, Newman, Ravinovich, Ziegler, the so-called GNRS conjecture, that asserts that the gap is constant for all H minor free graphs. And currently, the best lower bound that we have is a lower bound of 2 for the planar case by Lear and Raghavendra. And the upper bound is square root log n by the result of Rao. Now, what is this object, the ellipsis random partition? So let me briefly define this. So suppose that you have a metric space. We want to obtain a random partition of the set of points into clusters so that the following two conditions hold. First of all, the diameter of each cluster is upper bounded by some input parameter r. So we need to be able to do this for all r. And moreover, for any pair of points, the probability that they are separated is at most linear on the distance divided by r. Well, there is a multiplicative factor beta which quantifies how good the partition is. So the smaller this parameter beta, which is called the modulus of decomposability, the better the partition. And consequently, the better the approximation factor that you get if you use this method to route LP relaxations. So let me discuss briefly an example. So suppose you want to partition the metric space, which is the Euclidean line. So how you can do this is take intervals of length r and then randomly shift them by some uniformly chosen parameter. Now you can show that the modulus is exactly 1, which is best possible. Now, Klein, Plotkin, Rao, in some sense, extend this idea to H minor free graphs as follows. So if you have a graph that excludes some minor of size t, then you do a similar partitioning scheme looking at the BFS layers starting from some arbitrary root. Okay, so you randomly shift the boundaries of the BFS layers, and then you recurse in its connected components. And what they showed, surprisingly perhaps, is that by repeating t times, you obtain clusters of bounded radius. So this is roughly the key idea here. Now, so this is very nice for the planar case. So what we study is the directed case for planar graphs. Now, in order to do this, we need to consider a generalization of partitions. So the notion of partition does not make sense for the directed case. So let me explain why. So a partition of a metric space can be thought of as a symmetric transitive reflexive relation on X. So what is this relation? Every pair of points that end up in the same cluster are related. Now we extend this notion by considering the exact same definition and dropping the symmetry. So what we end up with is a different type of relation, which we refer to as quasi-partition. So it's a transitive reflexive relation on the set of points. So it turns out that this is the right object one needs to study if we want to understand rounding of LP relaxations of directed Sparsest-Cut and related cut problems on directed graphs. Okay, so formally, the definition of Ellipsis random quasi-partition, which goes back to some prior work that was focusing on graphs of bounded tree width. The definition is as follows. So you have it's exactly symmetric to the symmetric case, completely analogous. So you have a quasimetric space, and we get a random relation R such that it satisfies the following two conditions. So the probability two points are, in a sense, separated is small, and at the same time the diameter of every cluster is small. Of course, now here the diameter of a cluster is not, it does not really agree with our intuition from the symmetric case, so this is the precise definition. So the main technical result of this paper is to show that the modulus of decomposability in this directed case is bounded by a constant factor for, So the main technical result of this paper is to show that the modulus is bounded by a polylogarithmic factor, precisely log square of n, for the case of quasimetric spaces that are obtained as shortest path metrics of directed planar graphs, or simply planar quasimetric spaces. Alright, now let me say a few words about how the proof is obtained. So on the technical side, we combine ideas that were invented by Thorup for the problem of designing compact approximate distance oracles. So these are data structures that can very quickly report approximately the distance between any pair of vertices. And we combine these techniques with the key random partitioning scheme invented by Bartal in his paper for embedding metric spaces into random trees. So what is interesting here is that Bartal's approach also is useful in the directed case in our setting. Now, let me say a few words about how these two key components are combined. So first, Thorup's result, roughly speaking, can be thought of as consisting of two main steps. So the first step partitions the graph into slices of bounded thickness. So what do I mean by this? So on the figure on the left, we choose an arbitrary root And then we look at all vertices that are that can be reached from the root within some distance. And then on the second layer, we look at all the vertices that can reach the first layer within bounded distance. So we alternate between these two. So the directions of the shortest paths alternate. So this is the first step. Now you can show that the problem can be reduced to its slice. So somehow if you can obtain a good partition for its slice, this is good enough. So this is the key insight from Bartel. Now moreover, each one of these slices is now structurally, or if you wish, topologically nice in the following sense. So you can find balance separators that consist of a constant number of shortest paths. So this is nice now because in order to reduce the problem further, it is enough to be able to somehow remove these path separators. This allows us to do divide and conquer on each slice. Now to do this, we adapt the approach of Bartel for random partitioning. So this is an approach where one randomly grows balls of exponentially distributed random radii. I will leave the details for the paper. So this is all I want to say about the high-level idea of the proof. Now, and this is really the main technical result. Now from this one immediately obtains the rest of the theorems. So in particular, apart from the approximation algorithms, we obtain an interesting result for the theory of bi-ellipsis embeddings. So we can show that all planar quasimetric spaces embed into direct L1 with distortion log square of n. So and this is here, the notion of direct L1 was studied for directed cut problems by Charikar, Makaritsev. All right, so let me conclude with some final thoughts. So this is the first polylogarithmic approximation algorithm for any class of graphs, directed graphs of super constant tree width. Our techniques extend to the H-3 case, although this is not included in the paper, but it will be follow-up work. An interesting question now is to improve the gap that we obtain. The obvious question is whether the gap is constant. However, this seems to be a rather challenging question because, in particular, it implies the planar embedding conjecture. So it would also be interesting to see if it is easier to show lower bounds for the directed planar case. There is some quite powerful machinery, particular certain notions of coarse differentiation that have been invented for showing lower bounds for this type of embeddings. It would be interesting to see if these tools can be extended to our case. Thank you for your attention.